Hi guys, my name is Ashley Colchado and today I will be talking about my lab 1 on constant velocity. The purpose of the lab is to observe an object that is moving at a constant speed in the same direction. We use the lab in order to help gain a better understanding of Newton's fundamental principles. We use a tracker to analyze and obtain data of a real-life example of an object moving at constant speed, and then we use this to create a computational model of an object moving at a constant speed in GlowScript to compare the observational tracker data. Newton's fundamental principles. First, we use Newton's first law, which states that an object will stay at rest or in constant motion unless external force is added upon it, where F net equals 0. And then Newton's second law that states an object's acceleration is based on the object's mass and the force being applied, which is F net equals mass times acceleration. Some formulas that we use for the lab, we use the velocity formula, where the final velocity is equal to the initial velocity plus F net over mass times delta t, which is the change in time, and then the position formula, which is the final position is equal to the initial position plus the average velocity times delta t. And then down there is the main formula in our computational model, which is just position plus velocity times delta t. This is our experiment where we just rolled an exo marker along a meter stick. Some specifics, our system is the marker and the surroundings is everything else. And then the initial conditions, there's our initial position as you can see, and then our initial velocity was 100. This is the computational model that I used, and I just copied the code that was provided and I changed certain things to match my observations. I did not change the mass because the mass would not affect the calculations. I did change the initial conditions for the position, the velocity to match my observations. And then I also changed the delta to 1 over 45 because this needed to match the number of frames that was in my video. So this was 1 over 45. And then this is the second half of the computational model where the only thing I really changed was the ending time of the loop to match my observation, which is 1.5. And then I believe I also edited the momentum principle, which was like the final formula that we used, which I talked a little bit about earlier. Here is my model where I plotted my data for the observed versus predicted. And as you can see, the observed position increased over time. It also increased slower than the predicted position. And the two lines were close at first, but became further apart. And as you can see, the observed data leveled off towards the end, and the predicted model continued increasing at a constant rate. Some possible errors for this could be that the tracker may not have been accurate, which caused data to be inaccurate. There may have been additional forces acting upon that system that we didn't take into consideration. And then the camera angle or the calibration could have been causing errors in measuring the marker's position. So what if the plus x or the negative x were interchanged? The directions of motion would be reversed, and then the position values that were positive would become negative. The shape of the graph would stay similar, but it would reflect across the x-axis, and the observed and predicted lines would still show the same difference in motion, and this would only change the sign of the position, not the overall trend. What does this mean? The experiment helps demonstrate the general idea of constant velocity, but it doesn't provide a perfect, accurate real-life example. In the real world, it's nearly impossible for a moving object to experience a true net force of 0. It's just difficult to account for every push and pull acting on an object and confirm that they completely balance out. And then external forces such as friction and air resistance could affect the object's motion and prevent net force from being 0. That's it. Thank you.